today's session, we will talk about structure spectrum correlations. Basically, what we will do today is we will look into the spectra of simple molecules and try to see what kind of features we get in the spectrum and try to correlate them with the structure of the molecule. The session is planned as follows, that is, to begin with, we will try to briefly review what we did in the previous sessions. Thereafter, we will look into kind of recall again the salient features of NMR spectra. Having done that, we will come to the main theme of today's session, that is structure spectral correlations. Essentially, we will look into spectra of simple molecules, and towards the end we will try to sum up what we do in today's session. So, with this brief outline, let us try to quickly recall what we have done so far. What we have done so far is, that is, we have explained NMR as a phenomenon that we have been doing for quite some time now. Having done that, we went on to talk about the methods to recall NMR spectrum, and then thereafter we outlined the characteristics of NMR spectra and their significance. We talked in detail about all the characteristics, and then we explained the basis for all these characteristics and the factors which affect them, like the characteristics like chemical shift and things like that. Okay. So, that has been done earlier. Now, to make case for a kind of basis for today's session, let us quickly recall what are the salient features of NMR spectra. There happen to be 4 such features. The first one is that is the number of different signals, because in NMR spectra you get number of signals over there. The number of different signals in NMR spectra indicate about the different types of protons present in the molecule. Let us look at some examples here. So, this is simple methanol here. So, we see here that we get 2 signals here which are indicative of 2 types of protons in the molecule. One is a methyl proton, one is an OH there. Another molecule, say ethanol. So, here we get 3 kind of signals here. We are not getting into details of the splitting of the pattern over there. In general, there are 3 signals over there. So, they are indicative of 3 different types of protons in ethanol molecule. Another molecule here, look at this case here. So, in this case, we are just getting 2 signals over there which are indicative of 2 kinds of methyl protons over there. This methyl is attached, linked to a carbon atom which is attached to a oxygen here, whereas this methyl group is attached directly to an oxygen atom here. So, this will come somewhere here low field, and this will be coming at high field over there. So, essentially it amounts to saying that the 2 signals indicate that there are 2 different types of protons in the molecule. Yet another example here. So, in this case what we see is that there are only 2 kind of signals coming there, one small signal here and this is a large signal over here. This essentially is because of 2 types of protons here. So, these 2 terminal methyls are equivalent. So, they will give me only one signal here, whereas this methylene group here will come out as a small signal over there. So, again there are 2 types of protons. So, the basic point I want to bring home here is, that is, the number of signals are indicative of different types of protons there in the molecule there. The second feature we have learnt earlier is, that is the position of signals, that is chemical shift. The chemical shift tells about the electronic environment of a particular proton in the molecule. Let us look at some examples here. Say ethanol here. In case of ethanol, we got 3 signals. We talked about ethanol spectrum n number of times by now. So, what you see here is that there are 3 signals over there. Now, which is which? This signal here, the smaller one here for one proton, this is coming quite downfield, because this is because of this proton here which is attached directly to an oxygen atom. This is an hydroxy proton over there. And whereas this CH2, the methylene is coming somewhere here, and this terminal methyl group is coming at high field over there. So, essentially it tells me that the 3 protons here, the 3 types of protons in ethanol molecule are of having different electronic environment around them. So, that is the positioning part of it. Yet another example here. So, look at this molecule here. In this case, again I am getting 3 signals indicative of 3 types of protons and also the location of these signals over there. So, you find that this CH2 will come downfield over here, because it is attached directly to an oxygen atom over here. This methylene will come at this position here, whereas the terminal methyl will come highest field over there. So, essentially this indicates the electronic environment. Yet another example here. So, in this case what you find is that this methylene group here, which is attached directly to bromine atom, will come quite downfield here, whereas this central methylene will come somewhere here, and this terminal methyl is coming high field over there. So, what I want to bring home here is, that is the location, the signal's position here, the chemical shift is indicative of the electronic environment here, because primarily here in these examples we are looking it into the effect of electronegativity of the substituent over there, because this oxygen of bromine atom, they are electronegative atoms. So, they affect the chemical shift positions of the neighboring protons over there. Okay. The third feature happens to be the area under the peaks of different protons. They provide information about the ratio of number of protons of different types. Let us look at this. Now, in this molecule here, the spectra what we see is, if you look at the area under the peaks over here, we find that happens to be in the ratio of 2:2:3. That means, this basically is the same ratio as it is of these protons here, 2:2:3 here. So, the area under the peak gives me the so called integration, gives me information about the number of protons of different types there. And the fourth feature we have learned earlier is called as a spin-spin splitting or spin-spin coupling. Essentially, what happens is, different signals what we are getting, they split into series of number of lines over there. And look at this spectrum here, again I am talking about ethanol. You find is that this signal has split into 4 lines here, whereas this is into 3 lines. So, the 4 lines indicate that there are 3 equivalent neighbors here. 3 line spectra indicate there are 2 equivalent neighbors over there. So, it is n+1 rule, which we discussed in detail in the previous session. Now, having recalled the salient features, let us go further and look into the spectra of simple molecules. That is the main theme of today's session, and let us see what kind of information we gather from the spectra and how I am able to correlate the spectra with the structure of the molecule. Let us look at very simple molecules to begin with. Let us look at the simplest possible molecule, maybe the methanol here. Methanol is a simple molecule here. What you find is that there are 2 signals coming there. We talked about this earlier also. These 2 signals tell me that there are 2 different types of protons over there. But what you find is that this one proton here, that means this signal is because of one proton here. This basically is the signal because of hydroxy group there, this OH proton here. Whereas, this is your 3 proton signal is basically because of the terminal methyl over there. So, essentially what you find is the hydrogen attached to the oxygen atom gives a signal at low field. That is one rule of the thumb. That means, any proton which is linked directly to an electronegative atom will come downfield. That is one thing we have to learn. Another thing probably we can learn from this spectrum is that typically this methyl protons will come higher field, they will come around 1 to 2 ppm or so. In this case, since this carbon atom is attached to an oxygen, so this is coming relatively downfield. I am not putting the numbers over there. The objective here was to give you the relative positioning there. Let us look at the spectra of ethanol here. In case of ethanol spectrum, we can learn a few things here. One, typically what we learned in the case of methanol as well, that is this the lowest field signal for one proton is because of this proton here, which is attached directly to the oxygen atom. It is obvious, because attached to a oxygen atom which is electronegative, it will kind of de-shield the proton and it will come at low field there. Now, these methylene are coming somewhere midway, much downfield as compared to the methyl protons here. Here again it is so because these methylene protons are attached to a carbon atom which is attached to an oxygen atom which is electronegative, and these methyl protons are farther away from oxygen. So, they are coming at their typical positions of about 1 ppm or so. Another thing which we have to look at, a salient feature, a typical feature here, a typical pattern what to say is that this pattern of 2 proton quartet and 3 proton triplet, this is typical of an ethyl group. We will come across this pattern very often, and this is indicative of an ethyl group. This will become very handy when we are trying to interpret the spectra of larger molecules there. Let us move further, look at ethyl bromide. This is another example which gives me a typical pattern of 3 line and 4 lines here, a triplet and quartet of 3 protons and 2 protons respectively. It again is an example of ethyl group there. Let us move further. Let us look at some hydrocarbons now. The spectra of ethane is very simple. It is just one signal here, because what you find is in case of ethane there are 6 protons and all of them are equivalent. So, since they are all equivalent, they will give me only one signal there. So, I get a signal somewhere around 0.9 or 0.8 ppm, and that is a typical position where the alkyl protons are observed. The range for alkyl protons is about from 0.8 to 1.5 ppm. That's where we look at the hydrocarbon part of it, or rather the saturated hydrocarbons which are there to be observed in this range there. Now, let us move to a slightly more involved molecule, that is of ethene. In case of ethene, what you find is, in case of ethane the signal was somewhere around 1 ppm. In case of ethene, it has moved to about 5.2 ppm. It is a drastic change there. This drastic change basically is because of the anisotropic effect of this double bond over there. You will recall that we learnt about anisotropic effect earlier, wherein in this case of ethane molecule, when this molecule is oriented perpendicular to the applied field, it generates a field, and that field augments the proton over there, and as a consequence what you find is the signal goes downfield there. It is a typical anisotropic effect. So, the message from this particular spectrum is that any unsaturation will lead to a downfield shift of the signals there. Let us go further and look at the spectrum of ethine, that is acetylene. In case of acetylene, again there is one signal here because it is a symmetric molecule, it comes around 1.8 ppm. This effect again we explained in terms of an isotropic effect here, wherein the molecule of acetylene aligns with the applied field and generates a magnetic field which opposes the protons there. So, as a consequence they come at a position of about 1.8 ppm. The important thing here is that is an isotropic effect. And one more thing which I would like to bring home here is, that is, just keep these numbers in mind. Acetylene typically around 1.8 ppm, ethylene around 5.2 ppm. So, they are the typical values for these molecules, and any ethylene or any unsaturation will come somewhere close by. Okay. So, these numbers will become very useful later on. Okay. Let us move further and look at dynamic spectrum of benzene molecule. Benzene again is a very highly symmetric molecule. This gives me one signal at about of 6 protons at about 7.27 ppm, which is a characteristic value for benzene. And this again you will recall we discussed earlier that this again is because of the anisotropic effect. Here again, because in case of benzene and similar molecules, what happens is these kind of molecules sustain some kind of a ring current because of the kind of alternating single and double bonds. They generate some kind of a ring current, and as a consequence the field which is generated is such that it opposes, it kind of augments the field at the protons, and these protons go highly downfield, and typically all aromatic protons will be observed somewhere around 7 to 8 ppm. So, that is one characteristic of aromatic protons. Okay. So, that means if I look at a spectrum and find that there is a signal somewhere around 7 to 8 ppm, this is a good enough indication that my molecule contains some kind of an aromatic moiety there. Let us look at the molecule of toluene. The spectrum is like here. Now, what you find is, in case of toluene, there are a few things we have to take note of, that is, there are 2 signals coming there which are indicative of 2 kind of protons. This is a low resolution spectrum here. This 3 proton signal is because of the methyl group here, and then this 5 proton signal is because of the aromatic protons over there. So, we observe 2 things here. One, that these aromatic protons are coming somewhere around 7 ppm, that is what I mentioned earlier, that is aromatic protons will come somewhere between 7 to 8 ppm. And second thing what you observe is, this methyl group is coming at around 2.3 or 2.2 ppm. And typically we mentioned earlier that these hydrocarbons or methyl groups typically come around say 1 ppm or so, 0.8 to 1.5 or so. In this case it is coming beyond 2, and this coming beyond 2 is because of the neighboring aryl group over there. This benzene ring is responsible for this downfield shift over there. So, this again is a good enough indication. That means, if I have got some kind of a hydrocarbon kind of a group coming there, and that shifts little downfield, that is indicative of some kind of a electron withdrawing entity over there. Okay. So, the methyl groups are observed low field due to the benzene ring. That is a message from this particular spectrum here. Please keep all these things in mind, because they will become very useful when you try to interpret spectra, but that we will be doing in the next session. Okay. Let us go further. Look at toluene, because we just mentioned we have got 2 line spectra there. What you find is, if I go a little high resolution spectrum, I find that these aromatic protons are not equivalent what you find is there are number of splittings coming over there, and this is because of the fact that the protons which are ortho to this methyl group are different, having different electronic environment as compared to that of the meta and then the para one there. So, they come at different positions. What you find is the spectrum is not one line spectra, it is a little more involved one. We are not getting into the details of that here, but the message I want to convey is that these protons are not equivalent. Let us move further, look at the spectra of paraxylene. Paraxylene is this molecule, we all know that. Now, what you find is here again I am getting only two signals there. One is for 6 protons, one is for 4 protons. 6 protons are coming because of these 2 methyl groups over there. And why are we getting 2 lines here? Because this is a highly symmetric molecule. So, because of symmetry, if I just have an axis of symmetry over here, so all these 4 protons of the aromatic part here, they all are equivalent. That is why they are giving me one signal around 7 ppm. And these methyl groups are coming around 2.2 again, that is typical of these methyl groups which are linked directly to an benzene ring over there, and that effect we just discussed earlier. So, 2 signals are observed because of the symmetry there. Had there been no symmetry, there would have been more signals. Let us go to a related molecule, that is of orthoxylene. In case of orthoxylene, what we have is, we find that here again we are getting 2 signals. What typically we expect here is, we expect many more signals there. We expect one signal for these 2 methyl groups there. So, 3 plus 3 6 protons here, we are getting that. Then we expect one signal for this proton here and this proton over here, which is ortho to the respective methyl groups there, and then one signal for this. I expect 3 signals, but I am getting 2 signals. This is a typical case which is called as accidental equivalence. That means, these protons are expected to be different, but they happen to be accidentally they happen to be equivalent, and what we get is, we get a signal for 4 protons as against 2 signals for 2 protons each. Now, in the light of this spectra of say benzene, toluene, paraxylene and orthoxylene, how many signals do we expect in case of metaxylene? Let us look at this. In case of metaxylene, I expect one signal for this proton, another signal for these 2 methyl groups there, because they are equivalent, because again a symmetric molecule, again one signal for these protons and one for this one. So, we expect 1, 2, 3, 4 signals there, and that is what we get here. The spectra gives me 4 signals, and the typical positions of this protons comes at 7.01 and these 2 come at 6.96, and this methyl groups come at 2.27, and then this proton comes at 6.94 ppm. So, we expect 4 signals and we are getting 4 signals, and in case of orthoxylene, getting 2 signals was an accidental case there. That is, it happens to be so that the protons behave like equivalent protons, otherwise they are expected to be different there. Okay. Let us move further. Let us move further and look at another related molecule called as mesitylene. In case of mesitylene, what you find is, this is a highly symmetric molecule, and in this case what you find is, all these protons 3 methyl here, 3, 3, all these 9 protons are equivalent here. So, they give me one signal for 9 protons at a typical position of 2.2. I am sure that by now we have seen so many examples that any methyl group attached to an aromatic ring, to a benzene ring, will come around 2.2 ppm. So, register this number in your minds, because this will become very useful. And second, what you find is that these 3 protons here, which are on the benzene ring here, so these 3 protons are again equivalent, and they are giving me one signal for 3 protons at about 7 ppm, little below 7 ppm. So, that is typically an aromatic proton there. So, we are getting 2 signals due to symmetry again. So, the message from this and some of the previous examples is that if the molecule is symmetric, then the number of signals what you observe will be fewer than what are typically expected otherwise. Okay. Let us look at one more spectra here, say para tertiary butyl toluene. Now, look at this molecule, what are we getting here? What you are seeing here is that I am getting a large signal for 9 protons. This 9 proton signal is because of this tertiary butyl group over there. So, because these 3 plus 3 plus 3, these 9 protons are equivalent, and since there is no neighboring proton over here, this is just a carbon atom. So, I get singlet here for 9 protons there. Then I am getting a 3 proton, again a singlet here, and this is because of this methyl group here, which is attached directly to the benzene ring here. So, again you look at this methyl group, since attached directly to the benzene ring, is coming at about 2.2 or 2.3 ppm, whereas these methyl groups which are attached to the benzene ring through a carbon atom, so they are coming at the typical position of about 1.2 ppm. That is where the aliphatic protons are expected. As against these two things, the aromatic part of it, we find that there are 4 protons coming there, and these 4 protons are coming in groups of 2 each. These 2 protons ortho to tertiary butyl group will be different from the ones which are meta to that. Okay. So, essentially I am getting 3 signals, and this is, there is more to this, not a one signal, this is a combination of signals because of these 2 groups over there. Okay. So, the important message from this particular spectrum is that tertiary butyl group gives you a 9 proton singlet. That is one. If we come across any molecule, look at the spectra, we find a large singlet for 9 protons, typically an indication that you are looking into a molecule having tertiary butyl group. This characteristic of that. Okay. So, and secondly, in this molecule the aromatic protons are not equivalent, as just mentioned here. Look at ethyl benzene. I am sure that by now we know what to expect here. What to expect here is that we have got a benzene ring which is monosubstituted. So, all these 5 protons will come somewhere around 7 ppm, we are getting it there. Then this methylene group which is attached directly to the benzene ring will come somewhere around 2 ppm or 2.3 or 2.2 ppm, it is coming somewhere around 2.5 ppm, and this terminal methyl group is coming at about 1.2 ppm, the typical position for an aliphatic proton there. A few more things probably we can make note of here, that is, out of these 2 things here, this methyl is coming at a typical position, and this 2 proton methylene is coming at 2.5 or 2.6 ppm because of this benzene ring. Another thing which probably can note of is that this CH3 CH2 is a typical ethyl group there, you are getting a spectrum of ethyl group there. So, this is coming as a 2 proton quartet, and this is a 3 proton triplet over there, and this is a kind of a multiplet kind of a spectrum there, which indicates that these protons are not equivalent. Okay. So, 2 things, characteristic pattern of ethyl protons, or this alkyl should be read as ethyl protons, and the aromatic protons are not equivalent here. Let us move further and look at another spectrum, say of ethanoic acid. In case of ethanoic acid, what you find is we get just 2 signals there, a 3 proton signal here at about 2 ppm, and we are getting one signal which is at about this is written here, this is about 9.8 here, and this is about 2.4 ppm offset. When we say, if you look at a spectrum and there is some kind of an offset, offset means whatever is number given over here, this number is added to the position of the signal there. So, in this case the signal is at 9.8, offset is 2.4. So, 9.8 plus 2.4, that makes it 12.2. So, this signal is coming at 12.2 ppm, and that is typical. That is typical of acidic protons there. Carboxylic acids will typically come beyond 10 ppm. So, that is again something which is very important to take note of, that is any molecule which gives a signal around 10 ppm, 10, 11 or 12 ppm, that indicates the molecule has an carboxylic group in that. And rest is simple, this methyl group is coming at about 2 ppm, because this is attached to a carbon atom attached to electronegative oxygen atoms over there. So, this is not coming at 0.9 or 1 ppm there. Let us go further, look at another molecule, acetaldehyde. Now, in this case what you find is, again I am getting 2 signals, one for this methyl group there around 1.2 ppm, and then this signal is around 9.8 ppm. This is typical, around between 9 to 10 ppm is the position where a aldehyde group proton will come over there. This single proton will come somewhere around 9.2, 9.4, 9.6, between 9 to 10 ppm. That is a typical position where an aldehydic proton is observed. So, that again is something which has to be taken away from this particular spectrum, is that is the aldehydic protons are observed around 9 to 10 ppm. Let's go further and look at one more molecule, that is of tertiary butyl methyl ether. The spectrum is something like this. In this case, what you are getting is again just two signals there, because there are only two kinds of protons in this case. What you find is that tertiary butyl, again another indication here, tertiary butyl, all these 9 protons, 3 plus 3 plus 3, they all are equivalent. They are coming at say around 1.2 ppm as one singlet here, 9 proton singlet. And this OCH3, that means this methyl group attached directly to an oxygen atom here as an ether linkage here, is coming around 3.2 ppm. That again is a very typical value of O methyl. So, this also, suppose you have a spectrum and you get a signal for 3 protons somewhere around 3.2 or 3.4 ppm, that is an indication that you are having a molecule which is having a methyl ether there. So, O methyl comes around 3.3 ppm or so. Look at this molecule here. This is 2-chloropropane. In case of 2-chloropropane, what you are finding is that we get again two signals here, one for 6 proton, one for 1 proton over there. This is again a very typical pattern to look forward to in case of NM spectra, because what you are getting is, look at the structure of molecule here. So, these 3 protons here of this methyl group and these 3, because this basically is an isopropyl group over here. In case of isopropyl group, these 6 protons are equivalent. So, for this proton here, there are 6 neighbors. So, this single proton comes as a septet here. This is a 7-line spectrum here. Whereas, for all these 6 protons, there is only one neighbor here. So, what you get is a doublet here. So, a 6 proton doublet and a 1 proton septet is a typical pattern to look forward to for isopropyl group. That means, in other words, if I have a spectrum and we get this kind of a pattern there, that is a 6 proton doublet and 1 proton septet, we are for sure that we are dealing with a molecule having an isopropyl group there. So, there are patterns, typical patterns to look forward to. Okay, let us go further. Look at benzyl alcohol. In case of benzyl alcohol, what you are getting is 3 signals over there. This is just the numbers are not here clear. So, this is basically about 7.2 ppm. This is my aromatic part of the molecule. Benzyl alcohol is benzene CH2 OH there. Now, this is the methylene protons over there and this is my OH here, 1 proton, 2 proton and 5 protons over there. And the typical thing which you have to take note of in this particular spectrum is that this signal here for 1 proton, which is an OH here, is coming little broad signal, and that happens. That means if we have a molecule and we get 1 proton signal which is broadened, that is an indication we are having an OH or an NH kind of a proton there. Typically OH and NH come as broad signals over there. And of course, the second thing we should take note of here is, that is the methylene protons are quite downfield here, is coming around 4.5 ppm or so, that is quite downfield here, because of this methyl group is attached either firstly to benzene ring and also an OH group there. So, the two effects are adding up together to give me a signal which is highly downfield there. Had it been only benzene ring, would have come around 2.2. Since oxygen also is attached directly to that, it comes further downfield around 4.5 ppm there. So, let us sum up what you have done. What you have done today is basically we reviewed the contents of previous session and then thereafter we outlined the salient features. Then thereafter we came down to the main theme of today's session, and in that what we have done is that we have looked into a broad array of different kind of molecules and we have seen the molecular structure and also the corresponding NMR spectrum. And from these two things we have tried to find what kind of correlations are there. That means typical things we have to look forward to, say for ethyl group we know what to look forward, for isopropyl group what to look forward, where do I expect a proton from an aldehyde, or where do I expect acidic protons, where do I expect hydroxyl groups there. So, all these things we have picked up from these spectra, and all this information we will try to put together into some kind of a, we will devise some kind of a strategy to interpret NMR spectra, because today what we have done is we have taken spectra of known molecules. We know the structure, we have the spectra, we are trying to correlate the two together. Now, in the next session what we will do is, in the light of this we will formulate a strategy, then thereafter we will look into the spectra of the molecules We know the molecular formula, but we do not know the structure. Using this the NMR spectrum, we will try to find out the structure of molecules using all this information what we learned today. With that, we will close for today, and the next session we will talk about how to interpret NMR spectra in terms of the structure of the molecule there. Thank you.